imaging, but you can kind of see the slide that I'm on here from the angle that I've got. And you can hear me talk, so hopefully that will be helpful, but I'm going to try to do a video recording here. It's actually mirroring my screen, but I'll see if I can't figure out a good way to fix that. All right. So before I start on the chemical level of organization, I did say the most abundant compound, inorganic compound, was water in the body, but I didn't really talk as much about water. So really quickly, let's just finish up last week's PowerPoint and talk a little bit about the properties of water. Okay, first of all, we said water is a polar molecule. It has a partial negative charge on the oxygen end and partial positive charges on the hydrogen end. That is because oxygen is the more what atom? What's the word that we used? Do you remember that? Electronegative. What does it mean to be more electronegative? You're greedy with electrons. You have more electron withdrawing power. So if any time you looked at the placement of electrons here, they would more likely be around the nucleus of oxygen than hydrogen. So it's more greedy. So it makes these slight partial charges that are changing back and forth. And this is why water is liquid at room temperature. So again, if we've got these water molecules here, if the white, my little Mickey Mouse here, are hydrogens, the red is oxygen, they're constantly breaking apart and reforming bonds, sticking to one another. I'll actually pass these around because I know it's hard to see up here if you guys want to see them. But these are just little water molecules. They have magnets in them, so they stick. But that polarity of these water molecules gives them particular properties. So what do we call the type of bond between the hydrogens and oxygens of adjacent molecules of water? What type of bond is that? Not polar covalent, because that's within it, but what is between two water molecules? Hydrogen bonding. Those are the ones that are easily broken, those attractions between those partial charges. So because of these partial charges, water is a good solvent. So if I make it a little map here on the board, several properties of water, it is a good solvent. A solvent is a liquid that dissolves things. So here we see water with a block of sodium chloride salt. Since sodium chloride salt molecules are held together by an ionic bond, it can pull apart those charges. So things with charges or things that are polar can be dissociated in water. So it's, a great solvent. Now something else water is good at, cohesion. I talked a little bit about this last week. I'm going to say cohesion is water molecules sticking together due to hydrogen bonding. So water molecules sticking together due to hydrogen bonding. So I said, have you ever seen like a little water spider, they call them? I don't know what they're called, but they sit on top of the water because the water molecules stick more to one another than the air-water interface, than the air molecules. So this is an example of cohesion, where this might come in as important in your body. What if someone has pneumonia? What's going on in their lungs? They've got liquid down in the bottom of the lungs. It makes it harder to breathe, right? Maybe you have had pneumonia, maybe you haven't. But it makes it a little bit harder to breathe. That's because what's happening is the cohesion of water molecules down in your lungs. Every time you inhale, you have to break the surface tension of the water molecules. So you must inhale a lot harder to break that surface tension because of that cohesion. So there's a good biologically important example, or physiological important example of cohesion. All right. Water is also used in chemical reactions. It's a better black marker. What you see here are two very important reactions. If you want to put two things together, you can pull a water molecule out between them and stick them together. That's called dehydration synthesis. So notice right here, we take an OH off of this molecule and H off of this one, and we have H2O. When we pull water out, now look at our resulting product. We have one thing. So we've got dehydration synthesis. So removing water sticks things together. And then we can take the reaction the other way. If you notice this from last week, this is a reversible reaction. You've got a hydrolysis reaction that pulls things apart. So if you add a water molecule, it pulls these two molecules apart. I think of it this way. If you get a water hose and you spray it at a block house that you've made, you'll knock it down, right? So break that word apart, hydrolysis. Lysis means breaking things apart. So dehydration synthesis, hydrolysis, decomposition. So it's important in chemical reactions, and we'll see that today when we talk about our big macromolecules. That makes sense to everybody? And because of the cohesion of water molecules, that gives water a high heat capacity and a high heat of vaporization. I did mention this a little last week, but water having a high heat capacity, have you ever sat and tried to watch a boiling pot of water or a pot of water boil? Takes a long time, right? That's because water, unlike other things, can absorb a whole lot of heat before it starts to boil. Do you know why water starts to boil? Because you know how you have those little magnets right now you're passing around and you're moving them around with the little magnets? They start going faster and faster and faster until they actually start breaking the surface tension and boiling. But a lot of the energy, the heat energy, has to go into breaking hydrogen bonds, which it doesn't have to do for a lot of other things. So therefore water can absorb a whole lot of heat energy before it starts to boil. That makes it a good property in the body because it can absorb a lot of heat. That also leads it to have a high heat of vaporization. What do you think heat of vaporization means? Okay, there we go. So it turns into gas. Remember, we've got solids, liquids, gases. The more heat it absorbs, the more it's likely to turn into gas. That means that water on the surface of our body, when we sweat, can absorb a whole lot of heat before it dissipates. So therefore, whenever sweat evaporates from our skin, if we're really hot, it brings a lot of heat with it, which gives it a great cooling property. So it has a high heat capacity and a high heat of vaporization due to its chemical properties. And finally, just kind of a memorizer here. There's a lot of water in the body. It reduces friction between things. So one of the things we talked about in lab, I guess not last week, the week before, are serous membranes. And remember, serous fluid are in between serous membranes. Water is in between those, so it helps things slide over one another. And I feel like there's a glare up here, so I'm going to flip out another light. Is that a little better? All right. So that takes care of the PowerPoint we started last week. Now I'm going to start the second one, and mostly what we're going to talk about are big macromolecules of things like food we eat, but I have a couple other little things to finish up first. So, kind of going off of water, I said a solvent was a liquid that dissolves things. So, going off of that solvent, the solid particle we dissolve with the solvent, these markers are good. So if solvent is the liquid, and we dissolve a solid in it, it's called a solute, we get what's called a solution. Now a solution is a type of mixture. So a mixture is whenever you physically blend things together, but you're not actually creating chemical bonds, okay? So question, if you get sugar and you dissolve it in water, are you making chemical bonds or are you just making a mixture? You're just making a mixture. You're not changing the bond structure. You still have sugar water, but you're making a mixture. You're blending it in. So sugar water would be an example of a solution. Unless you just really saturate it with a lot of sugar, it's going to be clear and transparent because the solute molecules are small and completely pulled apart. So sugar water is an example of a solution. Now we've got two other types of mixtures. We've got things called colloids and suspension. Colloids are when the solute particles dissolve completely, kind of like sugar water, but the solute particles are so big, they scatter light. You can't see through it like it were just water. A good example is milk. Milk is pretty, what they call homogeneous, right? It's going to be white all the way through, looks like the same thing. And milk is basically big proteins that are in water, so there's water in milk. But you know why you can't really see through milk, why it's cloudy? Sorry? Okay, well, you've got a lot of calcium in there, right? But basically going from that, those big solute particles are too large and they scatter light. So milk is actually considered a solution too because it does have solute particles that are transferred throughout it. But it's also a colloid because the particles are large enough to scatter light. Now what if we went down to a pond and picked up pond water? Wouldn't there be lots of stuff in pond water? You ever seen that? The particles would eventually settle out to the bottom of the cup if you left it here over the weekend. So it would be considered a suspension. If we leave sugar water and milk out, it's going to look the same when we come back next Monday. But some things have big particles that settle out. Those are suspensions. So let's think about this. Which of these do you think would be a solution, colloid, and a suspension? Think about that for just like a couple seconds. You're welcome to share with somebody else if you want to. This one shouldn't be too hard. Which of those do you think is a solution? Salt water, okay? Because you dissolve sodium chloride, salt, and water, clear and transparent. What is milk? We just already said that one, right? Colloid, big particles that scatter light. And what would blood be? Suspension, it's the only one left. But if you leave blood out, the particles actually will separate because blood is watery plasma with blood cells and proteins in it. Okay? Be okay there? Awesome. Please stop me if you have questions. All right. Now, I'm not going to spend a ton of time on this. There's a little bit of math involved, but I want to tell you a little bit about concentrations. Concentration is how much of a solute is in the solution. Now, going back to my sodium chloride example, if I got salt and dissolved it in water, has anybody ever used salt water to gargle with when you had a sore throat? What happens if you just sprinkle a little salt in there and gargle it? Not much, right? Because you didn't put enough in there. But then what if somebody makes you a saltwater solution and they get half the bottle of salt and pour it in there? You're like, oh my gosh, I can't get all the salt out of my mouth. This is bad, right? So you have to have the right concentration. So that brings us to two different ways to measure concentration. The easiest is percentage, so the percent you put in there. And then another one we'll talk a little bit about is molarity. Now, if you take a chemistry class, you'll talk about this more, but I'm just going to do a brief overview so that you understand it. To find a percent solution, this is mass per volume. So basically, grams dissolved in liters. The number of grams of a substance per 100 milliliters of solution. So if you wanted to make a 10% sodium chloride salt solution, You would get 100 milliliters of water, because that's what our percentage solutions are always based out of. And you would dissolve 10 grams in it. Remember using the balances in lab last week? You just dissolve 10 grams of sodium chloride solution, measure that out, and put it in 100 milliliters of water. And you'd have a 10% solution. What if you wanted to make a 20% solution? How much sodium chloride would you measure? So 10 grams, or 10% solution, you measure 10 grams. So 20% solution, you measure 20 grams, right? Easy enough. Now, a molarity solution is a little bit different. They describe a molar solution as the number of moles per liter. So they say you measure 1 mole of a solute, so 1 mole of the solid particle in 1 liter of solution. So if we measured 1 liter, so you have 1 liter of water, you have to figure out how to make a mole. What is a mole? Okay, there's a little mole. This is not the mole we're talking about. The definition your book gives of a mole is the amount of any substance that has the mass in grams equal to the sum of atomic masses of all its atoms. Is anybody like, what in the world does that mean? Okay, that's like a huge, big, fat definition. Okay. This is kind of interesting. If you really said, I don't want to go by calculation, I want to measure out how many particles are in a mole, the number of subatomic particles, the number of atoms in 1 mole you would have would be 6.023 times 10 to the 23rd particles. That is an enormous number. That is 10 to the 23rd, so you have 10 times 10 times 10 times 10, 23 times. You basically have 23 zeros on there. A big number. They call that Avogadro's number. So if I put 5 different bottles of different solutions up here, and I said each of them were 1 molar solutions, each one of those, regardless of what it was, would have 6.023 times 10 to the 23rd particles in it. Pretty amazing that you can measure something like that and know how many particles are in it. Obviously, we're not going to count all those. So how you do it, what this basically means, the amount of grams you would measure out on your balance, you just add together all of the mass, or all of the atomic masses of that molecular formula. So sodium chloride looks like this, NaCl. You would look at the periodic table and say, what's the atomic mass of sodium? Then you'd look at chlorine and you'd say, what's the atomic mass of chlorine? So to show you that, let me pull up my a periodic table, not atomic table. What's the atomic mass of sodium? Can anybody see it from here? Probably not. 22.98. And the atomic mass of chlorine is 35.45. So if you add sodium chloride, you just add, what was that, 22.8 and 35.5. And when you add those together, you would get 58.44. So you add that many grams in a liter of water. And what ends up magically happening is you have a bottle with 6.023 times 10 to the 23rd salt particles in it, atoms in it. Pretty spectacular you could do that. Really weird. People have a harder time with that just because it is less tangible. You cannot physically see yourself measuring out that number. But all you have to do is add together the atomic masses. So let's practice that. Just with the person sitting next to you, and you may want to try this yourself, see if you can come up with how to make a 25%, so that's a percent solution of C6H12O6, this is glucose, okay? And then decide how you would make a 1 molar solution of potassium chloride, and how many particles would be in it, okay? Now, if you don't have your periodic table of the elements, potassium's atomic mass and chlorine's, I'm going to have to look it up. The atomic mass of potassium is going to be 39.1. and of chlorine is 35.5. All right, so I'll put it back up. All right, so see if real quick you can do this with somebody next to you. Rooms were like just deep instead of water. Sideways. What's that? And you don't have to multiply by this. It would just be, you just divide 74.6 grams and 1.5. So you dissolve 74.6 grams of liquid. And then the number of particles would just be, so they just kind of imagine. Nope. So we don't get into super chemistry here, just enough to understand it. Because obviously we cover like chemistry, 3-hour sessions, so we don't go into full on Yes.
Is that not down at 36?
Yep. That's it.
That's what she done.
You would just measure it out. I wanted to measure out 74 things. And she would just pour salt in there, potassium chloride, whatever it is, until it reaches 25% sugar rate.
She's ran it into
It says for percentage, you always use 100 milliliters. So you go 100 milliliters of water in graduated cylinder. And you would weigh out how much glucose. 25%. Then get your scale, your balance. Oh, you just add the weight. Then on the water, you choose salt. Salt. The glucose, not salt. So if it's 25%, how many grams of glucose would you put on your balance? So when it was 10%, I weighed 10 grams. So when it's 25%, how many grams? 25 grams. So you put 25 grams on a scale and dissolve it in 100 milliliters of water. Now you can get a job
It's just be 25 because you're trying to hit that. Yeah.
All right. So if your group went to lab today and I said your fast quiz is make a 25% solution of, this is glucose, sugar, okay? How would you make a 25% solution of glucose? How many milliliters of water would you use? 100 milliliters. How many grams of glucose would you put in there? 25 grams. You'd measure out 25 grams on your balance and just dissolve it. You'd have a 25% solution. Okay. How would you make a 1 molar solution of potassium chloride? How many different elements do you have in there? 2, potassium and chloride. So how many grams of potassium chloride would you dissolve in 1 liter? Notice molarity is a liter of solution. 74.6 grams. And how many particles of potassium chloride would be in that? 6.023 times 10 to the 23rd, even though we're not going to count them. Okay? We get that? Everybody think they could do like a quick math problem on that if there was one on a test? Some of you are like, maybe. Okay? All right. Now taking our solutions just a little bit further, so this will be easy for some of you. Some of you have heard of this before. How many of you have heard of pH and acids and bases? A couple of you? All right. So whenever we're talking about solutions dissociating or solutes dissociating in solution, we mean things that are pulled apart by water when you pour it in. There are 3 things that they may dissociate into. What we've been talking about is a salt. So here's our potassium chloride. If we were making our 1 molar solution, let's say we put our, whatever you said it was, 76.4 something grams in there. They dissociate into basically their 2 respective ions. What type of ion is potassium? Cation, right? What about chloride? Anion, okay? So this is a salt. Whenever something dissociates with an OH ion, a group OH negative, an OH anion, or when something dissociates into an H cation, a hydrogen cation, they are considered acids and bases, and they are very important. So, for instance, this is called hydrochloric acid. If I were just looking at that and wanted to know if it were an acid, I would see, okay, this dissociates into free hydrogen ions. Whenever something dissolves to make free hydrogen ions in a solution, it is an acid. Okay? So acids have a lot of free hydrogen ions in a solution, or they give off free hydrogen ions in solution. That's our definition of an acid. Anything that gives free hydrogen ions to a solution. A base, the definition in the book is anything that accepts free hydrogen ions in a solution. Explain that a little more. So if we say, drive me nuts. We say acids give off hydrogen ions, and bases accept hydrogen ions, or we could say, or give off OH. OH negative ions, they have a name. It's called hydroxide ions. So you'll use this through A and P. Anytime you see an OH negative here, that's called a hydroxide ion. Now making this make a little more sense. These things can accept OH negatives. These accept hydrogen ions. Because let's think about this. If we had a hydroxide, so if you have a base and you pour it in solution and it gives off a bunch of these, what happens when you put a hydrogen with an OH? What do you get? Water. So you have H2O. Do you see that? And that means it neutralizes it, okay? So bases are going to be things kind of like bleach. People have this misconception that only acids are harmful, but that's not true. This is why bleach can be harmful. It gives off a whole lot of hydroxide ions. So bases accept free hydrogen ions, and acids give off free hydrogen ions. Okay? So I have that listed here. Notice again, it's just basically the dissociation of a water molecule. That's where you get hydroxide and free hydrogen ions. So real quick again, just with the people next to you, look at this little group of compounds I've given you. And decide if each one is an acid, base, or salt. Okay? I'll give you like a minute to do that. So I just want to write them down in order, look at them, think about them. See if you guys can figure it out. If you're not sitting next to anybody, feel free to tap somebody on the back or turn around and talk to somebody else and see if you guys can agree on something. All right. Everybody got an answer here? H2SO4, the name of that is sulfuric acid. Is that an acid, a base, or a salt? Acid. How do you know it's an acid? Because it would pull off an H, okay? What about NaOH? This is called sodium hydroxide. Is that an acid, a base, or a salt? A base. How do we know it's a base? OH. And what will the OHs do whenever you stick it in a solution? They will accept hydrogen. Yes. Okay. HCl, hydrochloric acid. What is that? An acid. KOH, potassium hydroxide. What is that? A base. And what about calcium carbonate? That's a salt because it doesn't have hydrogen or OH. Okay. Now something else, just kind of an FYI. Things that give off hydrogen ions, we call them acidic. And things that give off OHs or accept hydrogen ions, we call them basic. Another word for basic is alkaline. So I don't want you to be doing your reading and get confused on that. So alkaline things means basic. Basic and alkaline are the same thing, okay? So if you read something and it says it's a very alkaline solution in the body compared to other fluids, and you're like, what in the world do they mean? They mean it's a base. It accepts hydrogen ions. Okay? So just some terminology. If you haven't noticed, there's a lot of terminology in A&P, and unfortunately, sometimes there's a lot of words that mean the same thing. So I'll try to point those out as we come to it. All right. So how you measure acidity or alkalinity? There is a number 7 in the middle of the scale, and it goes all the way to a pH of 0 and all the way to a pH of 14. The closer something is to 0, the more acidic it is, the more hydrogen ions it has. pH stands for potential of hydrogen. Now it may sound weird that if pH stands for hydrogen ion concentration, why, when it gets closer to 0, is it more acidic? Because more acids have more hydrogens, right? You don't have to memorize this, but basically this scale is logarithmic. Anybody remember doing logarithms when you took a math class? You're like, what is all this stuff? I have to do the E and the ln and the logs, all that, right? You don't have to go through all the math in here, but basically if you take the negative logarithm of this number, it's going to give you the biggest number. So when you look at this, basically what you should get from it 10 to the 0 and 10 to the negative 1 are larger numbers than 10 to the negative 14 up here. So this 0 is going to have a lot of hydrogen ions, 10 to the 0, but this 10 to the negative 14 is the smallest number. Does that make sense? Negative exponents are small. So that's kind of how this works. But anything below 7 is acidic. The closer it is to 0, the more acidic it is. So if you have something with a pH of 0, it is going to be a very strong acid. It is going to burn you, okay? 7 is neutral. If you get water in a glass and drink it right now, it's probably going to be around 7. Your blood has a pH of about 7.35, 7.45. So it's pretty neutral. When you get above 7, things become increasingly more basic or alkaline. The closer something is to the number 14, the more basic it is, the more hydroxide ions or the more ability it has to bind up hydrogens in a solution. So also, since these are logarithmic, when we think about the number of hydrogen ions, each number represents a 10-fold change. So for instance, a solution with a pH of 0 is 10 times more acidic than a pH of 1. Something with a pH of 0 is 100 times more acidic than something with a pH of 2. Something with a pH of 14 is 100 times more basic than something with a pH of 12, not 2 times more basic, because it's going in a scale of 10 each time. Kind of like our metric unit we did last week in lab. Does that make sense? So let's answer this. A solution with a pH of 10 is Blake times more basic than a solution with a pH of 8. What's the correct answer there? How many people say 2 times more acidic? Or I'm sorry, basic. How many people say 10 times more basic? How many people say 100 times more basic? I didn't see a lot of hand raises. Does that mean the rest of you are writing things down or confused a little? So they go on a scale of 10. So how many differences is there between 8 and 10? 2, right? So if it's going up 10 every time, 8 to 9 is how many times? 10. 8 to 10 is 100, right? 8 to 11 is 1,000 times more, right? You're just adding a 0 each time. So it's almost like you're multiplying each one by 10. So something with a pH of 8 is actually 100 times more acidic than something with a pH of 10, because it's closer to 7 here. Usually this is the basic scale, so I said it. Something with a pH of 10 is 100 times more basic than something with a pH of 8. And the closer things get to 7, the more neutral they are. That means they have equal numbers of hydrogen ions and hydroxide ions. This is why a water molecule would be neutral. It's got equal numbers. Okay. Here's some examples. Again, I said blood is pretty neutral. Seawater 7 to 8.3. Here we see stomach acid is a 1 to 3 pH. Is stomach acid considered a weak acid or a very strong acid? It's very strong. Excuse me. So the lining of the stomach is made so it's very protected, so that over time the stomach acid doesn't eat through your stomach. Lemon juice 2.2 to 2.4. Is that a strong acid or a weak acid? Very strong. Sometimes people can spray like lemon juice in their hair and like it, but it can actually be damaging, right? Because it is very acidic. Soft drinks 3.9. It's not as acidic as stomach acid, but it's still fairly acidic, right? So it's not close to water. Quite a bit of acid. Household ammonia 11.9. Is that very basic or a little basic? Very basic. Here we see milk of magnesia. What do you use milk of magnesia for? Neutralize stomach acid when you have an upset stomach. The reason for that? It's very basic, so it takes up hydrogen ions. Okay? So, blood has a pH of 7.5. How would you consider that based on a pH scale? How would you describe blood? Neutral. Sodium hydroxide, a 1 molar solution. How many particles does it have if it's a 1 molar solution? 6.023 times 10 to the 23rd particles. Yeah, it's a pH of 14. What is it? It's a base, and is it strong or weak? Strong base. Hydrochloric acid at 1 molar. That's a pH of 1. Strong or weak acid? Strong acid. So notice again, here's our summary. You put acid in water, it gives off free hydrogen ions. You put a base in water, it accepts free hydrogen ions, usually by giving off hydroxides. We get a thumbs up, thumbs down, thumbs in the middle. Questions? Okay. Now I'm not going to go into great detail about this. There's a good chemical explanation for it, but we're just going to know the name because it's important in the body. Your blood is used to do what? What do you mostly use blood for? Transport stuff, right? But we said blood has a relatively neutral pH. Really, that's incorrect. I meant to put 7.35. Anyway, it's about 7.35 to 7.45, so that's pretty close. But if we say blood is 7.35 to 7.45, but it transports stuff, it may have things like hydrogens and hydroxide, and we don't want its pH getting messed up every time we transport things because it has such a narrow pH range. So your body is going to be very reliant on things called buffer systems. All a buffer is something that resists a change in pH. Now this is something you will look at over and over in AP2. It's called the bicarbonate buffer system. And basically it's a reversible reaction that can proceed to take up free hydrogen ions or release them depending on the needs of the body. But that's basically what a buffer system is, just like a molecule or a compound that can exist in a reversible reaction so it can do whatever else it needs to. So a buffer, by definition, is a solution that resists a change in pH. If you have a pH 5 buffer system and you add a pH 13 solution to it, it should stay relatively at pH of 5. It shouldn't change. So if you have a buffer that is a pH of 3, what happens when you add something of a pH of 1 to it? Does it change? What's its pH after you add the pH 1? Still 3. If you have a neutral buffer at pH 7.3 and you add a pH of 13 solution, what's the pH of the buffer solution after you add the 13? Still 7.3, right? So buffers resist changes in pH. All right, so now we are finally on our macromolecules. What we are going to do for the rest of the chemistry chapter is basically do a little overview of organic chemistry. Now that sounds kind of daunting, but I always thought organic chemistry was way more fun than the other chemistry. One of the things that I like about this is we're talking about big macromolecules of food and things that make up your body. It's a lot more relevantly important, I think, to people because it has to do a lot with your physiology of food. It helps people understand all different kinds of diets a little bit better, all right? So when we're talking about organic chemistry, what's our most important element here? Carbon. Usually things that contain carbon. Now they're also going to contain the things that we said make up 96% of our bodies. Hydrogen, nitrogen, oxygen, sometimes sulfur, okay? So we kind of add that a little bit. But usually you're going to have hydrocarbon skeletons. That means that since carbon can make 4 covalent bonds, it tends to be able to make big chains, which is very important in the structure of the body, with hydrogens on them, okay? So carbon can make covalent bonds with many things, so it makes it a good structural molecule for your food and for the body. So I'm going to give you guys a little handout. On one side it says the scariest worksheet ever. We're not going to do that yet. So flip it over and you're going to have a chart. So we're going to start on the chart. So just take one, pass it to your right. So I'll just turn it around so you'll have the chart. So we're going to try to do these in order. So when we're talking about our big macromolecules, what does a macromolecule sound like it is? A big molecule. Okay. These are mostly going to be big macromolecules of food you eat. What are some of the big things that you think you eat? Any groups? Meats. What's the main component of meat? Proteins, right? So you've got proteins. Yeah, you could write that in your box. No, we're not going to talk about proteins first, so make sure you're on the right row whenever we talk about them. You can put them in any order you want. What else do we have? Carbohydrates, right? And by carbohydrates, I also want you to put a slash and write polysaccharides. Because that's what the major group is called, a polysaccharide. What if you go to Kentucky Fried Chicken? You have the proteins, but what about all the greasy stuff that's on the outside of it? What is that? Fats. So you could say fats dash lipids. That group is called lipids. And the last one we don't ingest a lot, but they're called nucleic acids. So that's going to be your fourth category. So those are the 4 categories you should write in your macromolecules there. Everybody see that? All right. Now, one we're going to kind of add on and talk about at the end, it doesn't have to go in your chart, is adenosine triphosphate. It's abbreviated ATP, and it's important for us to talk about in this chapter too because it is your cellular energy. Without energy, the cells die. Now, before we get started talking about all these macromolecules and filling out the chart, I want you to be able to recognize small little chemical groups that are on your carbon-containing compounds. And those little groups are called functional groups. Now, when we look at chemicals as they're written, you can have something known as a molecular formula or a structural formula. A molecular formula, let me write this up here real quick. Molecular formula does not tell you anything about bonding. It's just something like this, C6H12O6. It tells you how many of each atom you have, but it doesn't show you how they're bound, because that's called a molecular formula. So you know you have 6 carbon atoms, 12 hydrogens, and 6 oxygens here, right? So that's a molecular formula. The other thing you have is a structural formula. A structural formula not only tells you the number of atoms you have, it tells you how they are bonded. So you might have something like this. And I'm not going to draw it all out, but you get the impression. It shows you with little lines, these little lines mean bonding. So for instance, if you had CH4, that would be the molecular formula of methane, but C, with the hydrogens drawn out like this, would be the structural formula. These little lines, each little line here, represents a covalent bond. So I'm going to say lines and structural formulas equal covalent bonds. Okay? Push this up. So lines and structural formulas are covalent bonds. What we're going to see on these next few slides, and this is just a chart that's in your text, are functional groups. It is very important to notice that R is not standing for an atom. R just means the rest of the molecule, okay? So if this whole thing is a structural molecule and you have what they call a hydroxyl, which is OH, there would be an OH added to it, but all of the rest of this would be your R. R means a variable group, anything it's bonded to, okay? So it's not an atom. So basically anything with an OH is considered an alcohol, okay? The name of this group is called a hydroxyl. When you add a hydroxyl to something, it tends to make it hydrophilic. What does the word hydrophilic mean? It can't have electricity pass through because it's water loving. It means it dissolves things in water. So hydroxyls are added to things and usually they dissolve in water. You see an OH group on something. If you see an SH on something, that is called a sulfhydryl. Molecules with a sulfhydryl added to them are considered thiols. You tend to find these within proteins. They help stabilize their big shapes because proteins are big. Anytime you see a carbon double bonded, double covalent bonded to an oxygen in the middle of a molecule, so that's what these two R's are, or with an H in the middle, so that's the same thing. These are going to be called carbonyls. When it's in the middle of a big chain, we call it a ketone. If it has a hydrogen, so it's at the end of a chain, we call it an aldehyde. So double bond olds, carbonyl groups. If you have a double bond to a carbon with an OH, a hydroxyl at the end of it, COOH, that is called a carboxyl. Anytime you see a COOH like this on a big molecule, that means it's probably an acid because these lose that hydrogen really easy. These are called carboxylic acids. So that's one way to recognize an acid. It has COOHs on it. Anytime you see C double bond O with an O next to it, so basically this whole thing, that group is called an ester. They're in a lot of your dietary fats. And they're also in aspirins. So aspirin, pain reliever. This one is easy because it's the only one with a P, with a phosphorus. Anytime you see a phosphorus with 4 O's on it, 4 oxygens bound to it, that is called a phosphate group. It is most common in ATP. You're going to see 3 groups of these. That's what that means. Adenosine triphosphate. That's what ATP stands for. It has 3 of these phosphate groups attached to it. This one should be easy too because it's the only one with a nitrogen. When you see a nitrogen bound to 2 or to 3 hydrogens, that's considered an amine. These are going to be important in a compound we talk about called an amino acid today. So an amino group. So aminos have nitrogen in them. Now, what are you going to do with these? People look at these, they're like, I don't understand. These look kind of hard. Basically your job, this is something that's good to put on note cards and just, put the name on the other side and just go over it and over it until you know how to recognize it. These are called functional groups of carbon. They are not the big macromolecules, but you're going to see these throughout our macromolecules. They're important to recognize each time you see each of these groups because they will tell you something about the chemical properties. So you'll be seeing something and you'll say, oh, I recognize this. This is a carboxyl. That means that this molecule must be an acid because it's got a COOH on it. They help you recognize things, okay? It's kind of like a property of a compound, kind of like properties of a person. You'd say, oh, they have curly hair or blue eyes or brown eyes. We've been learning those things since we were little bitty, so we can point things out like that, and it sounds easy. But this is the same thing. It's kind of like personal properties of a big compound. Now, historically, when I've taught this, people hate learning the functional groups of carbon because they are kind of boring, I think. It's like, I'm just memorizing the letters together, kind of like alphabet soup, and trying to recognize them on a compound. And then I think when people see this big, stretched out, long structural group, or structural formula, they get intimidated because they're trying to find groups in them. So I've got a little activity that I want you guys to do today. If you flip this page over, your chart, it says the scariest worksheet ever. You've got some of the functional groups on the top. You've got a hydroxyl group, an amino group, ketones, C double bond O, PO4 phosphate groups, sulfhydryl, and carboxyl groups, COOHs. And then I have a whole bunch of structural formulas down throughout this worksheet. Now what they have done is they have given you a color to circle each functional group you find in there. I did not bring all those colors. I need to buy some more colored pencils. So you may have to kind of make up your own colors. That's okay. But I do have like little rubber banded colored pencils. So what I'm going to have you guys do, you may have to use a little less colors. That's okay. You remember the base groups that we got in some last week? Okay. You're going to get in those base groups and you're going to bring your worksheet. And together you are going to circle as many functional groups and name them as you possibly can. Okay? Then at the end we'll see who found the most. All right? That makes sense to everybody? So we're just going to try to identify them and name them. So it may take a few minutes. So go ahead and move into those groups. Was anybody not here when I assigned those base groups and you don't have one? All right. Did anybody have less than 4 people in your group? Raise your hand. I know like 2 groups did. You did? Okay. Where was your group? You raised your hand. Give me just a minute and I'll figure out where everybody's sitting and then I'll assign you to a group. So go ahead and get in your groups. Everybody remembers where they were at? And you can bring that worksheet. I'll bring some of these colored pencils around. So we're just going to try to identify some of those base, not some of those base groups, some of those functional groups. Colored pencils. Anybody not get pencils? You need more? So, you need how many people are in your group? 2. Okay, so you're missing here. You can be with this group because they're missing different groups. I'll give you guys some pencils. You didn't get some? You got some. So sorry I don't have all 6 colors. I figure we can improvise. So see if you can find, or see how many you can find on there. And name. And just in case it helps you, I did post this on Momentum. This is a group of your these are your functional groups. So these are what you're looking for. Without a lot. I just thought you could see this easier when I put out the lights. Yes. It is on Momentum. Yes, that is basically the question that shows its origin. So you can see that because if you had another bond, there's no H won't bond to something. It only bonds to this is why I have C. And ester. So ester looks like C to an O to an O. So this is a what's bonded to two oxidants? Here's an OH and here's an H. So you better know H and then an Here's a P, so no. You probably don't have them all. Which one has a double bond O? Does it go against this great? Is that sarcasm? Yes. Yeah. Great. Right. Yes. Those are the hard exactly. What I usually do. That's just Easter. The double bond O ones are the hardest ones. They look the same way. How's it go, guys? No, because it's connected directly to the carbons and not the lights. So that makes sense. the hydrogens are out to the side, because that line shows where, or that line shows where the line is. So this would not be it, they're just kind of there to throw you off. Okay. How's it going, guys?
It's going.
Okay, looks like it's going all right. So you've got a whole part box over here. You've got the wand over here. That should be part box. Got any questions? How's it going, guys? Oh, that's going all right. The hardest ones are the double bonds. So let's look at this one. This is C double bond. So what is COOH? Carboxyl. So that's that whole thing of carboxyl. C double bond O ones are the hardest one because they all look like they're some of them have some extra stuff on it. Looks like you're good there. It's this. Yes. No, because it has this, it gives it an extra part. So these are the hardest ones. Number one, what else is that? Where does it look like? Right, exactly. The C. Okay, so this one, actually each one is on this one. This guy. not a functional group. We found out that these are actually a lot of fats. It's called a hydrocarbon. They're basically So it's important to note that every single thing in here is not a functional group. So, okay, everybody look at your sheet and count up the number of functional groups you found. Okay, we're going to see who found the most. All right. Anybody raise your hand if your group found over 20? Okay, a couple of you. All right. If you found over 21, keep your hand up. If you found over 22, keep your hand up. If you found over 23, keep your hand up. If you found over 24, keep your hand up. Okay, there's only 24. All right, so we want to see who found the most. So let's review each one, okay? That first big compound on the left side, there were 6 functional groups in it. How many people found 6 functional groups in the first one? All right, give yourself a star. See who found the most. The second one, how many functional groups were in that second molecule that was over to the right from the first one? We're looking at the top row. 3. All right. What about the one on the right at the very top row? How many functional groups were in that? 2. What were the functional groups in that one? Amino and carboxyl, right? Okay. Actually, I'm just going to turn this on and show you answers here, okay? So be honest, see how you did. Grade yourself on this. I'm not going to put it in a grade book, but grade yourself. I think you guys here in the middle said you found the most, right? Maybe you guys found quite a few. How many did you guys find? You found how many? All of them, 24. You found 24. Okay, how many groups found all of them? You guys did, right? I'll bring you guys M&Ms after the break. If you want M&Ms. If you don't want M&Ms, just tell me. Yes for M&Ms. Okay. All right, I will give you a print off of this. I don't have the colors on it, unfortunately, so you'd have to go through and name them. But I'll give you a print off of the correct answers at the end of class, just so you have them, if you don't want to go through and circle them. But I wanted you to just practice finding these. How I usually assess this on the exam, I will just have some pictures of individual functional groups, and I usually have a matching, and I say, name the functional group. So you need to know how to identify those, okay? All right, so we made it to the middle of class. If you want to go ahead and take a 10-minute break, go ahead and do that. You can return back to your original seats when you get back.
Do you want your seat back?
Oh, sure. I don't sit down much in here. So. Does anybody have my water molecules, by the way, or did I get them back? Did I get the water back? Let's see the water over there. I do have other sheets. I can find them. Here it is. Thank you. Yes, that's what somebody else just asked me for. A couple extra. There you go. Thank you. I'll just lay some extra. That's okay. Usually I tend to see they're laying all over the place after I get them out. So it's okay. Need to buy some more colored pencils. Yes. Several people are asking for extra. of these groups over there working. Were you in this group? No. You're welcome. I think it did too. I don't know if it's because my assumption is this room is colder, so you go out in the hall where it's warmer, and you come back in and it feels colder. It is not a carboxyl. It is a, or yes, it is a carboxyl. What you're going to say is it's just, this is just a carboxyl. So you don't need to circle the ketone and hydroxyl. This is whole thing. Okay, there's 3 people that were in one of these front groups that I didn't get evidence to yet because I couldn't remember the group. 2 people. You guys. You're lying. Yes, I did. I remembered some people. I just couldn't recall who all was in it. Oh, yes. If you have my colored pencils, please hand it back. All right. Some of you already gave me some back. Colored pencils. Do you have colored pencils?
Yes.
I think I'm missing some colored pencils. They're less in the bag than when I started. So if anybody has them, please return them to me. All right. So, beginning again. We are now going to go back to this side of the sheet. So you should have had down your macromolecules, so proteins, carbohydrates / polysaccharides, fats and lipids, and nucleic acids. Whatever row you put carbohydrates, polysaccharides on, that's the one we're going to start out with. So your second column in this worksheet, put it in front of my video here, says function. So macromolecule function. For the function of carbohydrates, I would write provides or stores energy. That's the main function. So carbohydrate main function, provides or stores energy. And another thing you may write down, carbohydrates have carbon, hydrogen, and oxygen in a ratio of 1 to 2 to 1. So that's how you recognize some of the carbohydrates. They have carbon, hydrogen, and oxygen in them in a ratio of 1 to 2 to 1. So basically you have the same number of carbons and oxygens and double number of hydrogens in your macromolecule. Okay? Carbohydrates provide most of the energy for your metabolism. This is where we get the low carb diet popularity. Because if your body doesn't have carbohydrates, it's going to have to go to its second favorite thing, which is fat. It's basically training your body to burn the fat. So the third column says monomer. Let me define the terms monomer and polymer. Monomer is a small unit that makes up a big unit called a polymer. What does the prefix mono mean? One. Poly means multiple, if you don't know that. Think about like making a beaded bracelet. Anybody go to like a camp or something, they have all these little beads everywhere, and which is a nightmare with little kids, and there's beads all over the floor for the rest of your life. Think of each one of those little beads as a monomer. You stick them all together and make a beaded bracelet, you get a polymer. So the monomer of a carbohydrate is called a monosaccharide. Now you can fill this out in as much detail as you want, because this chart is for you to keep for your study purposes. But remember, I have these PowerPoints posted, so you could just go back and refer to this if you wanted. But monosaccharides are basically sugars that have anywhere from 3 to 7 carbon atoms in it. And we have some particular names of monosaccharides. Glucose, that is the main monosaccharide in your body. I may at least want to put in parentheses glucose under monosaccharide. It's not the only monosaccharide, so think about that as like a red bead. And there's other color beads on there. It's not the only one, but it's going to be the one your body uses the most. Fructose is a monosaccharide. That's the one that's found in fruit. So when you bite into a strawberry and it tastes naturally sweet, that's because of the fructose in it. Galactose is found in milk sugars. And then 2 important ones called deoxyribose and ribose. So those are the only examples there of the monosaccharides. So you've got 5 of them. But basically they are simple units that make up a big polysaccharide. So the polymer is called a polysaccharide. Now I'm going to walk you through this. This is just a summary chart. First of all, this is a picture of all those monosaccharides I just named. The one you're going to see most commonly in the body is glucose. Now let me describe what you're going to have to do on the exam. Remember when I said I'll show you some pictures of functional groups and you have to match? Within those, I'll also show you some pictures of the monomers and polymers of these 4 major macromolecules. I might show you some pentose sugars and some hexose sugars. Pentose means 5. So monosaccharides always have these ring-like structures. How to read these? Everywhere there's a bend in the sugar means a carbon atom. They just don't draw the C's. So there's 1, 2, 3, 4, and then they have this one drawn. 5 carbons in a pentose sugar here. And then 1, 2, 3, 4, 5, 6. There's actually 6 here as well. 1, 2, 3, 4, 5. But there's 6 here in this this hexose. So notice the ring looks a little bit different. They're structural formulas. So pentose is here with the 5. Hexose is here with the 6. That's the big difference. You are not going to have to distinguish the difference between glucose, fructose, galactose, ribose, and deoxyribose. So I'm not going to have you study what are all the tiny differences between glucose and fructose. Well, the HO and all this that gets into a lot of detail, right? Now, if you continue on and take biochemistry courses, you will have to do that at some point. But here, I just will show you pictures of these, and you'll call it the monosaccharide. Is that okay? And also recognize the names, glucose, fructose, galactose, ribose, and deoxyribose are monosaccharides, but you do not have to distinguish the differences between these. Does that make sense? I want you to know these names are all monosaccharides. If I give you a general picture of one ring-like structure not bound to something else, it is a monosaccharide. But you don't have to distinguish the tiny differences between each one. All right. Now, whenever you get 2 monosaccharides and stick them together, they become what's called a disaccharide. Notice 1, 2, 1, 2, 1, 2. Now, I don't know how you would record this on your chart. You may want to stick it as an intermediate between a monomer and a polymer, because carbohydrates are really the only one that have that. But a disaccharide are 2 monosaccharides put together. They're not really the polymer. They're not a polysaccharide, but they have individual names because they're important in the body. So if you get galactose plus glucose, they make lactose, which is in milk, right? If you get glucose plus glucose, they make maltose. If you get glucose plus fructose, they make sucrose. So what is important about this slide? Well, I'd recognize the names maltose, sucrose, and lactose, but you don't have to know exactly what two monosaccharides make them up. But what I do want you to notice about these is the bond that holds them together. The bond that holds two monosaccharides together is called a glycosidic bond, okay? So glycosidic bonds hold two monosaccharides together. Now let's look at how two monosaccharides form this glycosidic bond. Let me go back a slide that I skipped. First of all, when we look at these monosaccharides, I said know the names glucose, fructose, and galactose and recognize that they're monosaccharides. But the interesting thing is if you looked at the molecular formula, remember what the molecular formula meant? It just told you the number of atoms in each one. The molecular formula for each of these guys, glucose, fructose, galactose, is C6H12O6. Isn't that interesting? They have the same molecular formula, but the positioning of their atoms or their structural formula is different. There is a name for that. Things that have the same molecular formula but a different structural formula are called isomers. So maybe highlight that word. An isomer means that two compounds have the same molecular formula, same number of atoms, but their structural formula is different. That's kind of like if you go to camp and you're getting kids to make beaded bracelets. You give them the same size of a piece of string. You give them 5 red beads, 6 green beads, 7 white beads. They may all look different. They have the same components, but they may put their color of beads in different orders, right? That's kind of like an isomer. You put the beads in a different order, but it's the exact same components. Glucose and fructose are isomers of one another. They have the exact same molecular formula. They're both C6H12O6. So if you went through and counted all the carbons here, the benzene in the ring, the oxygen's the hydrogen, you get 6 carbons, 12 hydrogens, 6 oxygen in each one. But they're structured differently. Now, if we put glucose plus fructose together, looking at these disaccharides, what would we get? Sucrose, okay? Now here's something interesting. What did we say the molecular formula for glucose was? C6H12O6, right? What did we say the molecular formula for fructose was? It's an isomer, so it is also. Okay, does that make sense? So since they're isomers, they both are C6H12O6. So when we write it this way, it looks the same. When we draw them, they look different. So if we made sucrose, which means bonding them together, what would we expect the molecular formula of sucrose to be? So sucrose is these added, right?
2C6H12O6.
Okay, well we wouldn't say 2C6H12O6. We basically multiply them, so we would expect it to be C12H24O12, right? But here's the thing. That is not the right molecular formula for sucrose. The molecular formula for sucrose is C12H22O11. So we would believe it to be C12H24O12, right? But it's C12H22O11. What's missing here? 2 H's and an oxygen, which is what? Water. Why do you think there's a water missing in sucrose here? Remember what we talked about at the beginning of class? What type of chemical reaction puts two things together? Dehydration synthesis. Remember me writing that on the board? What does it mean, dehydration synthesis? You remove a water molecule to put things together. So, whenever we are bonding glucose plus fructose, you remove a water molecule, and then this oxygen comes together to form a glycosidic bond. So that's why when we put glucose and fructose together, the molecular formula is C12H22O11 instead of C12H24O12. We did a dehydration synthesis. We pulled the water out to stick two things together. Now going back, if we wanted to break sucrose into glucose and fructose, what do you think we would have to add to this bond? Water, right? And we would call that anybody remember what it means to break two things apart and add a water molecule? What do we call that reaction? Began with hydrolysis reaction, hydrolysis. So if we added a water molecule to this bond, it would break it back down into glucose and fructose. That makes sense? Also, I'll give you a little heads up here. Sometimes I ask essay questions on exams. I do ask you a lot about that stuff I just talked about, okay? So put like a star by it. Make sure you understand those things. All right, something kind of interesting. Sucrose is a monosaccharide. It is table sugar. They recommend you consume it in moderation because rises in blood sugar happen as it's metabolized quickly in the body. And it damages your teeth, causes tooth decay, for those of you going into dental hygiene. Anybody heard of artificial sweeteners? So you've got things like aspartame, saccharin, and sucralose. They have come up with artificial sweeteners because they provide the same amount of sweetness. They actually provide more sweetness, but they are not metabolized by the body. Your blood sugar doesn't go up because they just go right through your body. They also have been shown not to cause tooth decay. Now they also provide the same amount of sweetness using much less than sugar. I have to write these down because I can't remember them. But aspartame are things like NutraSweet and Equal. NutraSweet and Equal are 200 times sweeter than sugar. So if you put aspartame in a Coke, you would need 200 times the amount of that to make the Coke that sweet with actual sugar. A lot of sugar, right? That's only a small one. Saccharin is sweet and low. Sweet and low is 400 times sweeter than sugar. You can use 400 times less to get the same amount of sweetener. And there's still one that's even more sweet, Splenda. Splenda is sucralose. It's an artificial sweetener. It is 600 times sweeter than sugar. So the sweetness that you get with Splenda, you would have to add 600 times that amount of sugar to get that sweetness. Pretty amazing, right? I just think that's interesting. All right. I think I asked you this already, but during chemistry lab, Maria places sucrose, which is table sugar, in a glass beaker, adds water, and stirs. As the table sugar disappears, she loudly proclaims that she has chemically broken down sucrose into fructose and glucose. Is that what she's done if she dissolves it in water? No, she just made a mixture. So notice that you can add water to this bond and break glucose from fructose in a hydrolysis reaction, but just dissolving it in water is not the same thing. When you dissolve sugar in water, you're not breaking it into glucose and fructose. You're just dissolving the individual particles of sugar, like a mixture we talked about. Okay, finally, our polymer. Our polymer of a monosaccharide is a carbohydrate or polysaccharide. There are 3 polysaccharides here. You may want to jot those down. They are glycogen, starch, and cellulose. So those are your 3 polysaccharides. The most important one in your food is glycogen. This is what it looks like. Glycogen is just a bunch of glucose in a big chain. What types of bonds are holding each one of these glucose molecules together? You remember the name of the bond that holds sugars together? Or a pack of M&Ms, does anybody remember? Glycosidic bonds. Glycosidic bonds hold glucose together. It's made only of glucose. This is how your body stores energy. If you ate a bowl of Fruity Pebbles this morning before you came in, your body turns all the sugars you eat into glucose. That's what it likes to metabolize. It used enough for your energy. Now when you're sitting in class right now, it can break down some of the sugars it's stored up. But how it stored it was as glycogen. That's how sugars are stored in your body. So you have lots of this in your liver and your muscles. Starch. This is your major carbohydrate you eat. You may be thinking, well, if glycogen is what my body uses for energy a lot, I don't remember reading that very much on nutrition labels or anything. Because mostly the type of carbohydrate you eat are starches. Think about like potatoes and, it's in plants. Potatoes, breads, that type of thing. It's formed by plants from glucose. So starches are the major dietary intake. And then finally, cellulose. This is something made by plants. So think about celery. Lots of cellulose in there. Interesting thing about cellulose, this is kind of like your fiber. It is important because it provides bulk for feces, which means it allows it to come through the body. Okay? Allows you to go to the bathroom better. But you can't digest it. That's why it helps with feces, because it always comes out of the body. So it's important to provide bulk, but you can't metabolize cellulose. You don't use that for energy. Anybody heard people say celery kind of takes more energy sometimes to eat it than it actually provides calories? So it's a lot of cellulose. All right, questions about carbohydrates. We got through that one. All right. Okay, our next one we are going to, I'm going to erase these as we go to them, are lipids. Lipids are mostly fats. Something I want you to recognize about lipids right off the bat. Name a fatty food you would eat. Name a lipid. Sorry? Well, burger is mostly protein, but it probably has fat on it. So let's go with, did you say burger? Okay. What is that? Steak. Steak is also protein because it's meat. So we're naming proteins. But let's talk about, what was that? Butter. Okay, I was going to say, let's talk about, you go to like, I'm trying to think of a name of steakhouse. Longhorn Steakhouse. And they put like a big thing of like the whiskey butter on top of it, right? It's like a big, huge thing of butter on top of your steak. Okay, so if you've ever had butter or oil in a plate and you try to wash the dish, what happens if you try to wash dishes without enough dish soap? It just kind of blah. It doesn't mix with the water, right? It kind of sits on top of the water. It doesn't matter how much hot water you put on that plate. If there's a lot of butter on it, it just does not clean it, right? That's because lipids are hydrophobic, okay? They are made out of, and somebody asked me this earlier, they asked me what that group was. You had a COOH at the end of one of those molecules on that worksheet, but then you had carbon after carbon after carbon after carbon after carbon, and I'm not going to draw each one. And then you had hydrogens all over the place. Again, I'm not drawing all the hydrogen, but all hydrogens here. When you see hydrocarbon skeletons, that's what this is called, carbons bonded to each other with hydrogen on them, those are usually fats. Think about this. Carbon and hydrogen, they are neither one electronegative. They don't have electron withdrawing power. So these big skeletons of carbon with hydrogen are nonpolar covalent bonds. And that's what usually makes up a fat. This is why fatty things like butter and oils do not mix well with water. Oil and water does not mix, right? So therefore, fats are going to be nonpolar. They do not dissolve well with water. So, whenever you're writing down your function for lipids in that second column, several things. First of all, fats store energy. Your body prefers to use carbohydrates for energy. But if it doesn't have carbohydrates and you are on a low-carb diet, it will use fat, so it does store energy. I have a little cartoon. I need to add it to my PowerPoint. It shows a little fat cell. Fat cells are called adipocytes. And it's talking to another cell of the body. And it says, what do we do with this excess food? We have too much of it. We put things everywhere else. And he says, store it as fat. And then he says, but we've been doing that a lot lately. Don't you think we should stop? And he says, no, we might need that someday. So basically your body has, for air purposes, an unlimited storage space for fat. It doesn't matter what you eat. If you eat too much of it, it gets turned into fat. And your body can store it in places that you probably don't want it. So it is used for energy storage. That's why your body does that. Okay? The other thing I would write in the function They're very important in making up cell membranes. So we'll get to that one in a minute. So there's several different types of lipids. Energy storage and cell membranes are our two big ones here. All right. So one of our major monomers, well, our major monomer of a lipid is a fatty acid. So in the monomer, you can write fatty acid. Now, some of you are probably good at drawing things out, little examples or whatever. You may want to draw a picture of this thing, hydrocarbon skeleton. A fatty acid looks like this. Bunch of carbons with hydrogens and a carboxyl group on the end. That's a fatty acid. So you guys saw that in the biochemical worksheets a minute ago. A carboxyl group at the end and a hydrocarbon skeleton. That's a fatty acid. Now what you're going to notice, our fatty acids can be considered saturated, like this top one, or unsaturated. Saturated, that means that every bond on the carbon is taken up by hydrogen. That makes sense, right? So saturation means they're saturated with hydrogen. Notice whenever it's saturated, it is a straight line. This is an unsaturated fatty acid. Can anybody see the difference in this unsaturated from the saturated? Has a kink in it, right? What's causing that kink? You've got a double bond between carbons. Remember we said covalent bonds could be single covalent bonds, double or triple last week? Here we have a double covalent bond. We're missing some hydrogens. So these carbons are bonded to one another. The important thing, though, about double covalent bonds and unsaturated fatty acid is every time there's a double bond, you get a kink. That is important because guess what? When you have kinks in bonds, things become liquid at room temperature. So if you have a lot of unsaturated fatty acids in your fat, it is an oil at room temperature because it makes spaces between things where they don't pack on one another. But if you have lots of saturated fats, all the fatty acids within your food molecule are packed on top of one another. That's kind of like a stick of butter or shortening. They're solid at room temperature, right? Everybody get that? So saturated fats are solid at room temperature because they pack on top of one another like little sticks. Unsaturated fats with double bonds are liquid at room temperature because they can't stack on one another. They've got bends. They're like oils. Coconut oil is healthy for you, and you said it's solid at room temperature. A little bit. It probably has more saturated, but we're going to talk a little bit about things they can do to chemicals to make things worse. Yeah. So we'll get to that in just a sec. So what do they usually say is healthier for you to fry things in? Well, oils mainly. Oils, okay. Things that are not really solids as much at room temperature because of these bonds. Now, here's some more examples. Saturated. This is monounsaturated. This is polyunsaturated. The more double bonds, the better. Monounsaturated means it just has one double bond, one kink. Polyunsaturated means that it has two. So monounsaturated are going to be things like olive oil, peanut oil, canola oil, avocados. Pretty healthy. Polyunsaturated are things like sunflower oil, corn oil, soybean oil, even fish, fatty fish. Polyunsaturated fats like this have been shown to decrease heart disease, decrease the risk of heart disease. So they are healthy. These guys, saturated fats, increase the risk of heart disease. Now, whenever you add 3 fatty acids to what we call a glycerol molecule over here, three carbons with an oxygen here, these ester linkages, this is a glyceride. This makes a triglyceride. So we've got several polymers of fats, But on the polymer side for your lipids, the first one I would write is a triglyceride. The function of a triglyceride, this is basically the fat in your body. Protection, insulation, and energy. This is the most common fat you think of. Okay, so I told you this otherwise. A fat is solid at room temperature. They don't have kinks. Oils are liquid at room temperature. There are several fats that are called essential fatty acids. That means you have to eat them in order to get them, and they're very important for health. Your essential fatty acids are omega-3, omega-6, and what we call cis fatty acids. Now let me show you what a cis fatty acid is. This is a little bit of organic chemistry, but notice both of these molecules. What are both of these? They're fatty acids. What kind? Monounsaturated, because they've got one kink, okay, or one double bond. But the cis fatty acid has a kink in it. The trans does not, because your hydrogens are flipped. They have a double bond, but they still pack. This is not natural. This is what they call a trans fat. How many people have heard of trans fats? If you work in a laboratory, they learned how to take kinks in the double bond, oils at room temperature, put them under high pressure in a process called hydrogenation. So that's a hydrogenated fat, hydrogenation. And basically, they change this where they still have the double bonds, but they pack on top of one another. They do this because they last longer for preservation. Now, when they don't have a kink, do you think they destroyed the purpose of having unsaturated fats? Pretty much, because the purpose of having unsaturated fats was that they didn't pack on one another and they were oils at room temperature. That made them more healthy. But what they have done when they make a trans fat is they have made them very unhealthy. They have a lab-made packed fat. So trans fats are very unhealthy, again shown to increase the risk of heart disease. So cis fatty acids are good for health. Trans fatty acids, even though they have a double bond, are not. That's something they did by hydrogenation in a lab. All right. Now your question about sunflower oil, or not sunflower, coconut oil. I have not thought about coconut oil as much. It may be the type of double bond it is. I have heard coconut oil. It may be that coconut oil is better than some things, not as good as other types of unsaturated fats. But I will look that up just to see the detail. That's what I imagine it would be. It is better than like using lard. Maybe better than olive oil. Could be something like that. So anyway, I'll look up some of the detail because it is more solid. So anyway, so thinking question. Your best friend has decided to begin frying his breakfast eggs in margarine instead of butter because he has heard that eating butter is bad for his heart. Do you think that's a good idea? No. What is margarine? It's basically a trans fat. Okay, it's a lab-made fat. They still pack. It's still solid at room temperature. So is margarine better than butter? No. Still bad. Are there better alternatives? What are better alternatives for him? Using something like an olive oil or sunflower oil, or maybe not using an oil at all. What about getting one of those copper pans, right? Have you guys seen those? You're supposed to not use oil. I don't have one. I don't know. Your book mentions that too. So anyway. All right. Another one you can write down for a polymer of a fat is phospholipid. Those of you that were in my lab, I mentioned a phospholipid. Where do you find phospholipids in your body? The cell membrane. Now this is showing details. The fat is made of two fatty acid tails, which we know what those are now. They might be unsaturated, they might be saturated. Notice the head has a phosphate group in it. It makes it polar. Adding a phosphate group to something makes it dissolve in water. So the plasma membrane has the phosphate heads facing the outside of the cell and the inside of the cell where they can interact with water. But so your plasma membrane doesn't dissolve on itself, it's got these little fatty acid tails facing in the middle. Because your body environment is very watery, so it has to have these fatty acid tails. We call it the phospholipid bilayer. So phospholipids are important in your body to make up cell membranes. All right, and yet another polymer of a fat is called a steroid. You may have heard of steroids in different contexts. Some people think of steroids like anabolic steroids. You inject yourself if you go work out. Is that where people have heard of that sometimes? Basically what that is, anabolic steroids usually use things like testosterone, male sex hormones. Basically all steroids are, they are cholesterol, so this is cholesterol, which is a steroid, with some things added onto this. They're a modified form of cholesterol. So basically when we think of a steroid, you think of a cholesterol, which are 4 ring-shaped structures, and then you have many cholesterol-derived steroid hormones that look like it with this cholesterol as a base. There are many hormones that are involved in stress responses as well. Has anybody ever went to the doctor and got a like a steroid shot, or they put you on steroids if you have like an ear infection or inflammation? I don't personally like them. Some people do like them, but what are some of the side effects when you have those steroids? Do you say sweat? You get sweaty. Anybody feel emotional when they take steroids? And your heart starts racing. Long-term use causes more belly fat, that type of thing. So basically these are going to be part of glucocorticoids, which are released from your adrenal cortex, adrenal glands that sit above the kidneys, which are also steroid-derived hormones. So there are many different steroid-derived hormones. Cortisol, testosterone, estradiol, all versions of cholesterol. So cholesterol is used to make these guys. It's also used in cell membranes. Where else have you heard about cholesterol? Okay, in your heart, in your bloodstream. We'll talk a little bit more about that later this semester. I don't want to get into cholesterol too much, but they help transport things through your body, okay? And they help repair cell membranes. So that's another one of our fats. Now those are our 3 major fats. I just wanted to briefly overview some other lipid-derived things in your body. You have things called eicosanoids. These are going to be things called prostaglandins in your body, again released to make reactions in your body. Things called leukotrienes, which are used in inflammatory responses. So these are going to be things, again, that are going to be involved in like steroid type. You have some vitamins that are fatty, vitamins D, E, and K. So usually they put it in like a fatty capsule when you take those vitamins because they don't mix very well with water in your stomach. And then HDL and LDL, these are your good and bad cholesterol. I'm not going to get into the details right now about what good and bad cholesterol are because we'll do it later. But I will tell you HDL is good cholesterol, LDL is bad cholesterol. HDL lowers your risk of heart disease, and LDL raises it. So you want your HDL to be high and your LDL to be low. Basically, proteins coat fats so they can carry them through the body because fats don't mix well in the blood, watery blood environment. So that's what these HDLs and LDLs are. They're called lipoproteins because they're basically cholesterol lipidy mixes mixed with protein. All right, so that takes care of our fats. What questions do you have about fats? So the major one we think of is a triglyceride. That's the dietary fat. All right, proteins. When we think about the function of a protein, they do everything. They are found everywhere. You may not want to write down all of it, but here are some of the things that proteins do. They are structural. They are regulatory. They regulate things in the body. They protect. They are contractile. They cause muscle contraction. They can transport things, such as in your lipoproteins. And remember when I talked about an enzyme last week? What was an enzyme? Do you remember how to define an enzyme? It was a biological catalyst. It sped up reactions. Enzymes are made out of protein. So lean adults, that means low body fat, can have 12 to 18% of their body mass being protein. So proteins are involved in tons of things. They're involved in almost all cell activities. Proteins are so important. In our next chapter that we do, we spend a lot of time just talking about how your cells make protein. It's important to know how it's made. The monomer for a protein is called an amino acid. Okay. Very important to recognize here. The name amino acid. What two functional groups do you think are in an amino acid that you just learned? Amino, right? And the carboxyl, the carboxylic acid, if you remember that. Do we recognize those? This is the amino. This is the carboxyl. They're both bound to a carbon and bound to a hydrogen. And you have about 20 different amino acids. The R group is where they all become different. We are not going to memorize all of them. But again, if you become a biology or a chemistry major, you will memorize them eventually, okay? So we are not going to memorize them all in here. So this is what an amino acid looks like. You need to be able to recognize it. An amino group, a carboxyl group, and a variable group. Now in body fluids, you will notice that they look like this. The amino group has a positive charge, and the carboxylic acid lost its hydrogen and has a negative charge. We call that being ionized. So that's still an amino acid. Whenever the extra hydrogen is on the amino, looks like it almost came off the carboxyl. But whenever you put two amino acids together, they create what's called a dipeptide. And the bond that holds two amino acids together is called a peptide bond. So you may want to jot that down. Peptide bonds hold amino acids together. So when you have two amino acids together, it's called a dipeptide. What do you think you call it if you have three amino acids together? Tripeptide. What do you think you call it if you put a whole bunch of amino acids together? Polypeptide. Now, notice this reaction. We had amino acid plus amino acid. We get a dipeptide plus water. Why do you think that water is there? When we synthesize things, what do we remove? A water molecule. So we have dehydration synthesis, right? If we were proceeding the opposite direction, what would we add to this bond to break down the dipeptide into two amino acids? Water, hydrolysis reaction. You guys are getting it. So, what I would say for the polymer of a protein, I would say it would be a polypeptide. Okay. Now, I have a model in my office. I forgot to bring it. Think about this for a minute. Okay. Has everybody drawn an amino acid for their monomer, what an amino acid would look like on your little chart? Okay, if you haven't, draw in a little amino acid so I know that you know what it looks like on your chart as a monomer. And I'm going to go run and get something real quick because I want to show it to you. I thought I bought it. So, proteins are more complex than carbohydrates and fats. We don't just simply have a polypeptide and we're done. Couldn't be that simple, right? You've got a polypeptide. A polypeptide are a bunch of amino acids together joined by peptide bonds. That is called the primary structure. So polypeptide is their primary structure. We also end up in a protein with something called a secondary structure, a tertiary structure, and a quaternary structure. So, here's my little model of a protein. So first of all, what I've got here. Pretend like this big blue piece of styrofoam. This is a polypeptide chain. Each one of these is an amino acid. Here's an amino acid, and I have a whole bunch of them in there. Here's an amino acid linked to it, so they're linked with a peptide bond. Then we get another amino acid and add it. I'm not going to add all of them, but you've got many different amino acids we could add. If you really got into this, they have a whole key and you can pick the amino acids and you can decide which amino acid you want to add to your protein. But notice I'm just going to make some amino acids, some various ones, and I'm just going to stick them together. Okay, so I'm not going to do any more, but I'd have this whole chain filled up with amino acids. The amino acid sequence of your protein is called a polypeptide. It would be in a line. So here, that's my primary sequence. Our secondary structure, there are two options. It can look like this, it can look like this. What does that secondary structure look like? A curlicue, right? We call that a helix. What does that look like? Sheet of paper, right? So your two options for a secondary structure, this is its shape. It can either be they call it an alpha helix, or a beta sheet, which is pleated. See, looks like a sheet of paper folded for an envelope. I think I'm going to make mine an alpha helix. So what happens first with the protein after its whole polypeptide gets made? It starts to twist. Form a helix. Isn't this cool? I'm so excited to get a protein. I wish I had enough for everybody. That's a very ugly helix. Your body does a better job than me. So it would have amino acids all up it, and it would be in a sheet or an alpha helix, okay? But we're not done. It now has to get a 3D shape. So after you get an alpha helix or a beta sheet, it would become its tertiary structure, which is its 3D shape. Now it's hard to draw that on the board, hence my model. So now it's going to take that alpha helix, and it's going to kind of get a three-dimensional shape here. There it is. Now, it might end here if it were a simple protein. The thing is, proteins are the biggest thing in your body. They're the biggest macromolecules. They can get huge. Notice they made this tertiary structure and they made it look like a gray ribbon. Notice it is interacting with a blue ribbon here. Let's say that the college gave me more money than it did, and I had several bags of these proteins, and I had instead of just a blue one, I had a red one and a green one and a white one. If I stuffed them all together, that would be its quaternary structure. That is 2 or more polypeptide chains together. What do I do with my good marker? So its quaternary structure, 2 or more chains together. And you'll notice the big, more complex proteins in your body are several different polypeptide chains together. They call that a quaternary structure. Makes a big globe. Makes just a big structure with all the 3D structures together of different polypeptide chains. Okay. So proteins, in essence, are more complex than other things. And it makes sense because we saw they're involved in almost all the cell functions. So proteins are extremely important for your body. If you want to build a lot of muscle, what do you eat a lot of? Protein. So your body can build more muscle, more contractile proteins, because it's a large structural component of your cell. If you want to build your muscles, you have to build the muscle cells. To build your muscle cells and make the individual cells bigger, you need more proteins in them. Okay. So I have all this listed out. I just kind of drew them out. Primary structure, secondary, tertiary, quaternary. Also notice here, the 3D structure is held together by hydrogen bonds, ionic bonds, disulfide bonds, and little things called hydrophobic interactions. So notice if you see a big tertiary structure of proteins, you're going to see those little sulfurs in there, SH groups. That's where those are important. Now, proteins. Let's think about something that's made out of protein. Do you think eggs have a lot of protein? That's the example I use a lot. Homeostatic mechanisms have to keep your body's pH and temperature, so like your blood pH, we said earlier, was very narrow, about 7.35 to 7.45. It has to keep it very narrow, even though it transports things. And you need to keep your body temperature relatively stable. One of the biggest reasons for that is because you have so many proteins forming structures in your body. What happens to an egg if you put it on a hot frying pan? Starts to fry, right? And it changes the egg's chemical properties. It doesn't look different after you fry it. So if you have a fried egg, will it ever look like the unfried egg again? No, you changed its chemical properties. Same thing happens with your proteins. If they are too hot or the pH is too acidic, it does something called denature them. To think about denature, think about frying an egg. It changes its chemical property. What the definition of denature is the protein unravels and loses that 3D shape. It's not the same anymore. It's no longer functional after it's been denatured due to extreme change in environment. So that's usually extreme pH or extreme temperature. Now remember when we had the little chart last week of the activation energy? You need a little bit of energy to push the rock down the hill and get it started. Remember that barrier was lowered when we added an enzyme that was made out of protein? If you heat up an enzyme made of protein, it speeds up the reaction a little bit, right? So chemical reactions happen faster with heat. However, if it gets too hot, guess what happens to your enzymes? They denature. They change chemical properties and they don't work anymore. So I'll come back to this in just a second. But let's think about this question. A 4-month-old baby is admitted to the hospital with a temperature of 102 degrees Fahrenheit. Why is it critical to treat the fever as quickly as possible? Because all those little enzymes can be damaged at very high fevers. This is particularly important in babies, okay, where fevers can get out of hand a little bit more quickly. So it's critical to treat the fever as quickly as possible because a high fever can start affecting proteins like enzymes that cause important chemical reactions to happen. When you damage those enzymes permanently, then the problem is that they can't form those chemical reactions and you can have death. So that's why that's very important. A little bit about enzymes. We said they were a catalyst. Enzymes are very specific for the reactions that they catalyze. For instance, has anybody heard of people that are lactose intolerant? Maybe some of you are lactose intolerant. You can't drink milk products. There is an enzyme in the intestine called lactase. One way to identify enzymes, they tend to end in the suffix ase, ace. So lactase breaks down lactose, okay? They are very efficient. It breaks down lactose very well. When I say specific, lactase only breaks down lactose. It cannot break down anything else. And they are subject to cellular control. So the cell decides, how much lactase is going to be produced and when it is going to actually break things down. Sometimes enzymes are made up of protein and non-protein together. There obviously has to be a lot of protein in an enzyme. We call the part that's made out of protein an apoenzyme, and sometimes they'll have little cofactors, sometimes little minerals that help them work. So here's an example. Let's say this enzyme is sucrase. Sucrase is going to be specific for sucrose. We already talked about sucrose today. What does sucrose, a disaccharide, break down into? Everybody remember? Well, sucrose is sugar. But when you break it down, it's a disaccharide. It is glucose plus fructose, right? So, notice this is the enzyme. It has a very specific spot just for sucrose. That's the only thing that will fit in it. We call that the active site. Sucrose fits in the active site. The enzyme catalyzes the reaction and it transforms the substrate, so we call whatever goes into the active site the substrate, into our products, glucose and fructose. Now notice how efficient it is. When it gets done, it's not used up. It can go back and do the same thing. It is always specific for only sucrose, the enzyme sucrase, and it can be used over and over and over again. Let's say this is warmed up just a little bit. This is going to work better. But let's say you get a fever that's really, really high. What happens to the enzyme? Denatures, doesn't work anymore. So a little bit of heat is good, a lot of heat is bad. That's an enzyme. All right. Now, thinking about this step. In a metabolic pathway consisting of 4 steps, so basically, if we've got 4 steps, this is how it usually works in the body. You've got A, enzyme A transfers something into B, enzyme B transfers something into C, enzyme C transfers something into D, etc. Okay? So in a pathway consisting of 4 steps, how would decreasing the amount of enzyme that catalyzes the second step, so this one, affect the end product? So let's think about this. This is a pathway. You start out with A. Enzyme A catalyzes the reaction of A to B. Enzyme B catalyzes the reaction of B to C. And then enzyme C catalyzes C to D. If we reduce the amount of enzyme A, do you think we'd have more or less D at the end? Less, right? And this is usually how the body works. There's a whole metabolic pathway. So just affecting one little enzyme can affect something bigger in the end. All right. We are finally on our last macromolecule, a nucleic acid. All right? We have 2 major nucleic acids, DNA and RNA. Whenever you say function for nucleic acid, these are the major functions, but I would say just stores genetic information. That's the easiest way to say this. So the function of a nucleic acid stores genetic information. The monomer of a nucleic acid is called a nucleotide. If you're going to draw a picture, this is what a nucleotide looks like. Nucleotides have 3 parts. What do we call this group? Phosphate. This is something you've seen before. What does this little blue group look like? It's a sugar. This is one of those pentose sugars. Anybody remember the 2 types of pentose sugars we had? They were called deoxyribose and ribose. Anybody recall that? It's okay if you don't. We just talked about them today. But it's either deoxyribose or ribose. DNA contains deoxyribose. RNA contains ribose. So it's got a sugar, a 5-carbon sugar. And then the last one you haven't seen. The last one is called a nitrogenous base. Now there are 5 different nitrogenous bases. You don't have to memorize what they look like, but they're in 2 categories, purines and pyrimidines. Your 2 purines are called adenine and guanine. So this picture you have here is a purine base. They have 2 rings. That's what a purine is. So purine means it has 2 rings. A pyrimidine nitrogenous base has 1 ring. So the difference in this picture, it would just have 1 ring here. And you've got 3 different pyrimidines. You've got thymine, cytosine, and uracil. How I remember the difference between them? The letters for the pyrimidines spell cut, C-U-T. They're 1 ring structure. So all we're saying here, these are the 3 parts of a nucleotide, which is the mononucleic acid. They always have a phosphate group. They always have a 5-carbon sugar. And they're going to have 1 of 5 nitrogenous bases. The individual nucleotides differ in the nitrogenous bases they hold. So they're going to be a 2-ring, a purine, adenine or guanine, or a 1-ring, a pyrimidine, thymine, cytosine, and uracil. Now, we said the 2 major nucleic acids are RNA and DNA. This is RNA and this is DNA. So let's talk about some of the differences that we see between RNA and DNA. How many how many strands is in RNA? 1, right? How many strands are in DNA? 2. The other difference, both DNA and RNA have all of these bases except thymine is found only in DNA and uracil is found only in RNA. And you can see that here. In RNA, they have C, G, A, and U, so cytosine, guanine, adenine, and uracil. In DNA, they have C, G, A, and T, so the T and the U. Now, your book has a chart with a comparison of DNA and RNA. They've already had that done for you. We already talked about this. They differ in the bases. There's thymine highlighted in orange in DNA and uracil highlighted in orange in RNA. This should be obvious too. We had 2 pentose sugars, deoxyribose and ribose. When you break down the word DNA, it means deoxyribonucleic acid. So the sugar found in DNA is deoxyribose. The word ribonucleic acid, RNA, is just ribose. So the sugar they have is different. Number of strands, DNA is 2 strands like we saw, looks like a big twisted ladder, whereas RNA is 1 strand. I'm going to be good to you on the first test. You can mark out for now the rest of this chart. Now I will tell you we'll have to learn the rest of it in detail for Chapter 3's test, but we're just going through a major overview right now. So to know the differences, I just want you to know these top 3 things. The bottom 4 thing, the function types, how it's copied, and base pairing. We will talk about that, but I'm not going to talk about it for this test. Just to keep things simple. And then finally, this is not in your chart, but another important biological molecule is ATP, adenosine triphosphate. Which one of your macromolecules does ATP look most like? Sorry? Well, it's got a phosphate group, but what does this whole thing look like? Looks like a nucleotide, right? It's basically looks the same. It's got a ribose sugar. It's got adenine, which is like one of the nitrogenous bases. But instead of having 1 phosphate group, it's got 3. See this little squiggly line here? They drew it that way on purpose because these squiggly lines mean high energy. Every time you break off a phosphate from ATP, it releases a whole lot of energy. So ATP is the primary way for your cell to store energy. So again, ATP means adenosine triphosphate because it has 1, 2, 3 phosphate groups. If you add water, which is again hydrolysis, what we add to break down bonds, You can break it into ADP, which is adenosine diphosphate, it has 2 phosphates now, plus phosphate plus energy. So breaking off a phosphate group releases energy that your cell can harness and use for other things. Adding energy to ADP and phosphate sticks it together and makes ATP. So that's how your cell makes it. Okay. So, I had a little activity. Well, let's see. We've not got a whole lot of time. I'm just going to talk to you guys because this chapter takes a while. So I apologize that we didn't have as much time for activities for this. But again, it does take a little bit of time to go through these. I know that chemistry can be a little bit more daunting. So I will tell you, if you have trouble with it and you have questions, I will help you. I will help you, I will help you, I will help you. But you have to let me know, because otherwise I'm not going to come up to Ashley and send her email after email every day. Does this make sense? Do you get this? Can I answer questions for you? I can't do that for everybody, so you have to let me know. You can come by the Learning Center, you can come by my office, you can send me an email, you can give me a call. I'm more than happy to spend extra time and help you break this down and understand it. But again, I cannot do that if I don't know that you have trouble with it. So what I have for you, instead of having you guys do the end activity, I have something, I just have it already finished here. First of all, I told you I'd give you a copy of the answer sheet for biochemical groups. So these are all circled. I also have this chart, and you could have wrote whatever information you have in it, but I have pictures of the monomers and polymers. Now, one other thing I'm going to want you guys to do on the test, I want you to be able to pick out the functional groups. I also want you to be able to recognize the monomers and polymers of these 4 macromolecules when you see them in a picture, because you're going to see those all through A and P, okay? So be able to recognize those. And the last thing, I'm not going to take this up. You do have Wiley Plus homework you have to finish, so again, that's kind of a priority. But sometimes people ask me for an extra worksheet to practice on. So I have you a little extra worksheet at the end of this. I will post the answers later so you can check yourself, but this is just for you if you want to fill this out and see how you're getting it, okay? So I've got an extra little sheet there. Before I hand this out, a little bit about the exam next week. It is 50 multiple choice questions first, okay? That is 70% of the exam. 30% of the exam, I have 2 bigger essay questions. One of them is going to be over chapter 1, over those feedback systems, okay? I told you that after the chapter 1 lecture. You need to be able to give me examples of positive and negative feedback and name those components. If you like to write out the answers to that to make sure you understand it and email it to me or bring it by my office and say, did I write this out well and do I understand it? You can do that. You can write out your answer ahead of time, bring it to me and show it to me. You can't have an answer on your test, but you could write something out, make sure you understand it so you know what you're writing, and I can kind of correct you and tell you what you need, and if you had enough detail, I'm fine with that. Okay? The other one is going to be over the chemistry chapter. So those are going to be higher point questions. They're usually something like 10 points apiece, so you need to be able to understand those major concepts and write out the answers to them. And then the other 50, again, are multiple choice. Don't forget the Wiley Plus questions that are posted, and they're going to go through the next week. They end next Monday morning, and I have the reading posted for this as well already, okay? Unfortunately, this is a 3-hour class, so it's like having 2 classes sandwiched together. So next week we'll take the first hour and a half for the exam. Second hour and a half we have to start on the cell. So I'm sorry that we have to do something after that. But we do have to stay after and work on material after the exam. If you can remember, bring a number 2 pencil, because for the multiple choice I do use a scan broadsheet. Also, for some of the questions, like we're on the quiz, you know, for protons, neutrons, molarity, you can bring a calculator on this quiz if you want, okay? I can't remember if I ask any big numbers. You should be able to do the math manually, I think. But I will let you have a calculator. I will give you a periodic table as well to use. Calculators cannot be on your phone. Okay, so if you forget one, you can't use a calculator that's on your phone. Anybody have questions over the exam next week or anything we covered today? Questions for me at all? I think Again, make sure you study well for this. Go through your notes. Go through the outlines. Contact me if you need help. So I'm going to give everybody a copy of this. So again, answer sheet to the biochemical groups, some pictures of that filled out chart that you have, then an extra sheet. Yes. If you have any of my colored pencils, I think I got a little less back. Please give it back before you leave. Otherwise, if you don't have any questions, you are good to go. Yes, I'm sorry. There is a study guide posted for exam one. It's posted on the window. If you haven't seen that already. Yes, you sent me an email. So that's fine. Just come follow. Can you follow me to my office right now? Okie doke.